I'll connect another smaller mass that's called M2, and it will displace at the datum X2. So this part over here is going to give me omega M1. That's what we're seeing just now. If we have another mass that's attached to it, this other mass is going to give us another resonance frequency that I call omega N2. This part over here is what we call the undamped dynamic vibration absorber. Where does the vibration absorber comes about? Well, we were saying that from what we had seen before, this X1 response was given by this. It's multiplied by M prop, and then the determinant. We solve this already. Meaning K2 minus N2 omega squared minus K2 squared. So, just now we were saying that this machine was, if we hit at the resonance frequency of omega M1, then it will resonate. So if I want to make sure that it does not do that, that means I want to force X1 over here. So this X1 sine omega t. I want to force this equal to 0. So if this is equal to 0, that means we want no vibration from the machine. And why do we want such a way that the machine has no vibration? Well, that's because if there's vibration over here, then it will be transmitted to your foundation, and that's bad. We don't want any vibration to be transmitted to the foundation. That's why, as much as possible, let's try to make sure that this X1 over here is also 0. So if that's the case, that means your K2 minus M2 omega squared must be equal to 0. This part here must be equal to 0. And we can solve it. Omega equal to square root K2 over M2. So this K2 over M2, in fact, is actually your omega N2. Omega N2. So why is that so? That's because, wasn't it K1? Square root of K1 over M1, that's omega M1. So if you have square root of K2 over M2, that must be omega N2. So what is that? That is the resonance frequency of this top part of this. So what does this show us? It shows us that if I have a machine over here, if I want to stop it from vibrating and it's resonating, and I have no choice, I have to use that operating frequency, because that operating frequency is the one that allows me to run my things more efficiently, maybe. But unfortunately, that operating frequency hits the resonance of this. So in order to avoid that resonance, I add on one more string and one more mass at the top. This additional spring and mass at the top is going to transfer that resonance frequency from the machine to the top part. Now the top part will resonate instead of my machine at the bottom. So this is a very powerful thing. You convert a single degree of freedom system, that is your machine, convert it into a 2-degree of freedom system such that the top part will resonate, bringing away most of the energy from the machine. That one would resonate. Maybe that one is just a spring and additional mass. And then you can stop your machine from resonate. That's a very powerful thing. Not sure if you've seen some of the bridges. Sometimes in the bridges they have things like a damping and then a mass. because your breath may resonate at a certain frequency, single degree of realization. In order to prevent that from resonating, you add on a special enhanced to it to bring away that resonance so that this thing that you attach to it starts to resonate instead of the breath. Right? So it's a safeguarding feature you can use. So what I said that so if omega is known, your K2 and M2 can be selected. You can select them. Select them in such a way that it reduces your machine's vibration. To 0. And we call this process of selection K2 and M2. This is called tuning. So you tune your system such that your machine would result in 0 vibration, and then transferring most of that vibration to the second mass that you add on to that machine. So hence, K2 and M2, this sort of arrangement, this is called your undamped dynamic vibration absorber. So let's have a look at what happens to the X2 side. So if you want it to be tuned, so for that tuned system, what we need to do is to substitute your omega N2, which is square root A2 over M2, substitute that into your X2 equation. So X2 equation, previously we saw that is equal to this, K2 multiplied by F naught over determinant, K1 plus K2 minus M1. And this omega over there, omega squared over there, in our case is K2 over M2. And then multiplied by K2 minus M2 is also omega squared. So that will be K2 over M2 again. And then minus K2 squared. So that's substituting that omega squared with my omega N2. Because I'm interested to find out when that second mass is resonating, what happens to my X2 displacement. So if you work this out, you can see that this term over here, right, is K2 minus K2. So this whole term becomes 0. So you're left with K2 F naught divided by minus K2 squared. So that will give us minus F naught over K2. So this is the displacement of the mass that's at the top of your machine. So what is this negative sign? The negative sign, it implies that M2 is out of phase with your applied force F. And it has this amplitude. So probably I'll do a demonstration. So you can imagine this, right, is this spring. And then I put on a paper clip over here. It's like the M2 advance. Okay? So this string would vibrate, kind of like this way. Okay? So let's say if you have your friend, if you work too hard, let's say, got into a cedar vibrating. So in vibrating. So if your friend you find that is vibrating this shape is take a bite. Okay. Squeeze continuously. Okay. So what you need to do is to convert that single degree of freedom system into a 2 degree of freedom system. So that means you transfer all this vibration energy into this, and then you start to find that this part you start to resonate, and then you should start to oscillate, converting the first degree of freedom system into a 2 degree of freedom system. So this is very useful, very powerful. It's still attached. Another additional mass in the string, but you need to design it. This is an absorber. You need to design what is that string constant and what is that mass in combination. Then it will result in transferring, absorbing that resonance energy into here, and this will start resonate. So that's the concept. So, what if you're interested in So, what if you're interested in the if you're interested in this undamped vibration absorber, that you want to tune it for resonance. So that was what we had done just now. We tune it for resonance. So if resonance is desired, tune dynamic vibration absorber. May be added. So what that means is that your omega equal to omega m1 equal to omega m2, right? We're interested for the entire structure to resonate. So it's different from the other case where the machine, we wanted to have a zero amplitude and then transfer the energy to that mass that we added on top. What if we want this entire structure to resonate? That means your omega m1 is equal to omega m2. So what that means is that your input frequency equal to your resonance frequency. Now, some of you may be wondering, why would anybody want to resonate a structure? I thought we want to damp it, or we want to make sure that it has as little vibration as possible. Why would anyone want to resonate? I had one-year projects before where we're interested to vibrate a structure, or it's kind of like a cantilever. So what I do to the cantilever is that I have this piezoelectric material. So the piezoelectric material is a material that, upon stress, will produce electricity. So I would want to resonate this because I applied 2 layers at the top and the bottom of the cantilever. So if I can make sure that this resonates, right, then I can harvest a lot of energy. So that's why there's also that sort of design for the system to resonate. So in this case here, omega 1, omega n1 and omega n2 respectively is equal to square root k1 over m1. So this must be equal to square root k2 over m2. So that relationship, if you are able to see, is the same as expressing 1 over omega m1 squared equal to m1 over k1 and 1 over omega n2 squared equal to m2 over k2. And why do I write it in this 1 over that form? That's because later on I'll make use of this relationship. Just need to let you know that you see it up here. So omega n1 squared must be equal to omega n2 squared because of this relationship. So this implies k1 over m1 is equal to k2 over m2. So later on I'll make use of all these relationships, just writing it down here now. So for resonance, that means x1 and x2 must approach, both of them approach infinity. So if x1 and x2 approaches infinity, from what you have seen before, both x1 and x2 expression, their determinant is actually the same. This is their determinant. K2 minus m2 omega squared minus k2 squared equals 0. So again, this omega over here, these two omegas, this omega is the natural frequencies, right, of the machine. And the absorber system that's at the top, right, coincide with the operating frequency. That's where we want the whole system to be resonating. So since if we want x1 and x2 to approach infinity, so determinant must be equal to 0. I want to simplify this determinant by dividing throughout by k1 and k2. So dividing it throughout by k1 and k2, this term over here, divide by k1 and k2. So I'm going to split up that part. This divided by k1 and that part there divided by k2. And then this one divided by k1 over k2 will result in k2 over k1 divided by k1 over k2, so k2 and that k2 squared, that square cancel off, resulting in k2 over k1. So this term here, I'm going to multiply k1 or divide k1 inside. So it will result in 1 plus k2 over k1 minus m1 over k1 omega squared. Multiplied by this would be 1 divided by my term. So minus m2 over k2 omega squared. And then minus k2 over k1. So this term over here, m1 over k1, we had seen that somewhere before. m1 over k1 is 1 over omega m1 squared. So I'm going to replace that. So I'll get omega squared over omega m1 squared. And this one, m2 over k2, is 1 over omega n2 squared. So I have omega squared over omega n2 squared and minus k2 over k1. So there are a few things. We also know that omega m1 equal to omega n2. This can be written as omega over omega m1 equal to omega over omega n2. It's kind of like if you divide throughout by omega and then just cross multiple and multiply and then you get back to this expression. Why do I express this? Because I want to let this thing equal to R, where R is called my frequency ratio. Expressing the ratio of operating frequency with the natural frequency of the machine. And this must be equal to operating frequency over the absorber natural frequency omega n2. I call this R. Later on, I'll make use of a lot of R. And as I mentioned R, I want you to know that we are talking about the natural frequencies of omega 1 and omega 2. The same thing, this expression K1 over M1 must equal to K2 over M2. So if I do that cross multiplication, so I'll get K1 over K2 must equal to M2 over M1. Right, this is 2 and this is 1. So this, I also want to let it equal to something. I let it equal to mu. And mu here, I call it this a mass ratio. So now I can re-express this term over here. All this, I can re-express. This is 1 plus K2 over K1. K2 over K1, this is mu. Minus omega squared over omega m1 squared. This is R squared. And this 1, and this term over here is also R squared. Minus mu equal to 0. Much more simplified form. I can multiply this term by term in there. After a little bit of simplification, I get R4 minus 2 plus mu R squared plus 1 equal to 0. I call this equation star. Later on, I'll refer back to star. So this sort of equation is what we call a design equation. And later on, I'll tell you why is it called design equation. Now, we use it to solve something. To solve for two values of R. That is R1 and R2. Why do we have R1, R2 over here? That's because the R refers to the frequency ratio. And there are actually two of these frequency ratios. One is R1, the other one is R2. Later on, I'll show you why. And this R1 and R2, they are the natural frequencies. Of this machine and absorber system. So the natural frequencies, which is respectively omega m1 and omega n2. So R1 and R2 represents the natural frequencies of omega m1 and omega n2. So this is important to us. Now I want to break up a little bit to do a sketch. I'm interested to do a sketch using my x1 expression, which is k2 minus m2 omega squared multiplied by f naught. This was my x1 expression. Just writing down the determinant again. And this is a constant, and I can also multiply throughout by k1. So what I want to do is to express x1 divided by f naught multiplied by K1. Later on, I'll tell you why I have it arranged in this special way. So if I have this multiplied by this factor K1 over F0, so this F0 will be gone. And then this K2 here will become K1, K2, and minus K1, F2 omega squared. And divide by that determinant. So I think I'll start writing that determinant. It is always the same term over here. It's a determinant. The same as all this. So then what I want to do next is to divide the numerator and the denominator respectively by this factor. 1 over K1, K2. Right? Do that, do this. So K1, K2 minus K1, K2 omega squared, and the determinant. So if I were to do that, this term here will become 1. Minus, this term here will become M2 over K2 omega squared. And that determinant, when it's divided by K1, K2, this was the same case as the above. When we had determinant divided by K1, K2, so it results in this final form. So that's R4 minus 2 plus E R squared plus 1. That was a form that we had from the top. So this, we have seen before, M2 over K2, that is 1 over omega N2 squared. So what's going to happen is that this will be 1 minus omega squared over omega N2 squared. And divide by R4, 2 plus mu R squared plus 1. So we had said before, this omega over omega n squared is actually R. So this becomes 1 minus R squared over R power 4 plus mu R squared plus 1. So this whole thing is actually equal to x1 k1 over f1. I'm interested in this equation by plotting x1 k1 over f0 versus r, which is my frequency ratio. I'm interested in this. If I do the plot, and I'm just going to plot for mu that's equal to 1. Right? There are a lot of other mu values. And note that mu is your mass ratio. Right? The mass ratio, just now what we had was your M2 over M1 kind of mass ratio. Now, the value of your mass at the top is your M2 connected to M1. How big the value this is? If they are of the same value of these two masses, then mu is equal to 1. Right? So we are looking at that case now. So if I were to plot this, and particularly do the plot in modulus, then the kind of sketch I'm going to get is going to look like this. And go up. It's going to come down. It's going to go up again. Infinity. And it's going to come down.
Engine.
This will be 1. This will be R1 here. This will be R2 there. In this case here, all these dark solid line is for the case of mu is equal to 1. This frequency ratio is equal to 1 over here. What am I doing? What is all this?
Exactly.
If I put it into perspective, just now we have 1 degree of freedom system that is vibrating, and it's vibrating at a resonance frequency. Resonance frequency, we all know the frequency ratio is equal to 1, right? 1 degree of freedom system. Now, if I convert that 1 degree of freedom system into 2 degree of freedom system, then where are my natural frequencies? This is what's happening over here. It used to be resonating over here, so it used to have this kind of graph. It will go up and then come down in that way. In fact, this graph over here, for different mu values, it will look like that. Yeah. If you still remember, we had seen this equation before. That is 1 over square root of 1 minus theta squared. This square is at theta equal to 0. And then, that was the case. We have seen this one before. That was the case that is for 1 degree of freedom system. So when it hits at 1 on the frequency ratio, it will resting. 1 degree of freedom system. Now I convert that into a 2 degree of freedom system. Essentially, at that old resonance frequency, I'm able to split up into 2 resonance frequencies now, where this R1 is my first resonance frequency, and R2 is my second resonance frequency, because 2 degree of freedom system. So what that means in this graph is that it used to be that it's resonating at this point over here. It used to be that. But I would still want that operating frequency. And what I can do is to convert it into a 2 degree of freedom system, and hence that resonance frequency was split up in that way. And this point here is the point that I can operate now. So if there is that frequency, operating frequency that you need very badly, but it happens to hit the resonance frequency of the system, what you need to do is to add another spring and damper into a string and a mass to it, and then you will split it up, and then you can operate over it. How much it splits up, how far it is also another topic of interest. Let me finish this part first. So what I said just now is that for resonance, it occurs at R1 is less than 1, and R2 is greater than 1. Right? So we know that when the frequency ratio is equal to 1, we know that resonance occurs. That one we know is for 1 degree of freedom system. So, however, if we really want to operate at that resonance frequency, all we need to do is to add an absorber. And if we do that, it produces 2 resonance frequencies, omega n1 and omega n2. And this changes the dynamics to 0 displacement. So you can see here it becomes a 0 displacement. when your R is equal to 1, your frequency ratio is equal to 1.
1 dB of
These two resonance peaks, the two peaks of R1 and R2, is at R1, and particularly the case where mu is equal to 1. That means you have the mass of M2 equal to the mass of M1. You can substitute it in there, or mu equal to 1. Your R1 is actually equal to 0.618 over there. So, in the case of mu is equal to 1, mass ratio is equal to 1. And the other peak, R2, is actually equal to 1.618. Again, for this case of mu is equal to 1. So because of that, I'm actually interested to solve, to find out how my R1 and R2 will vary by plotting the plot of R versus mu. I want to see what other mu's would affect my R response, my resonance frequency response. So in order to do that, that means I need to solve for that star equation. And to solve for that star equation, we'll come back right after this.